So, following up from our last class where we showed that how scaling can be a very powerful argument, okay, let us now try to see that whether we can do things in a more proper way, right, more quantific way. So, what we are going to do over here in this particular part of the lecture is something called similarity solution. Okay. So, what is similarity solution to begin with, right? So, if you take a look. So, the basic idea is very simple. Okay, we will start with momentum and then we will try to see how it translates to the energy equation. Okay. So, let us put the two equations side by side. So, in case we need to refer it, we can do it quickly. So, this is the way. Okay. So, these are the two sets of equations. Okay. Of course, we have written just the x momentum equation, right, still it is within the boundary layer concept. Okay. So, we are still using the same boundary layer equations with whatever the caveats of the boundary layer equations are in this particular situation. Okay. So, the basic idea is very simple, right. Now, if you look at it, you will also get the whole thing. Okay. You will see that the boundary layer at say a particular location x1 looks like this. Okay. It is say the momentum. Okay. At a different location it looks very similar, of course it moves up like this, right, okay, because the boundary layer is increasing. Okay. So, basically x2 is greater than x1, correct, and if you go further downstream you will get that this profile will become more like that, right. Forgive my drawing, but it is, you can get the thing that x3 is greater than x2. Okay. So, all you can see that the profiles look very similar, right, looks very similar to each other, except that there are differences, but if you look at if you take this particular profile for example, okay, and if you stretch it, perhaps you can get this, if you stretch it further you can get this, right. So, it is almost like if we have a master profile like that, something like this, right. So, this master profile can be stretched like an elastic band, okay, and we should be able to fit this master profile to all these profiles that we have, right. Okay. So, the master profile, basically if we have to put it, the master profile can be stretched, it is almost stretched, okay, like an elastic band, okay, to fit actual profiles at any x locations, is not that so? Okay. And the same thing is valid for temperature also, right. The temperature is the same thing, the profile just looks a little bit opposite, but there also there is a master profile which you can stretch like an elastic band and you should be able to fit the profile. Okay. So, this gave an idea that they look very similar to each other, it is like those similar triangle concepts, right, that you have triangles which are similar, but they are not exact. So, what you do is you stretch it, right. So, that is how you get to make them exact, right. So, it is very similar. So, based on this the idea came that these profiles all look very similar to each other. Okay. So, is there some way by which we can take the x and y dependence, right. So, there is a x dependence, there is a y dependence of the velocity, right. As you can see the velocity, if this is the velocity profile, this has got both x and y dependence, right, because your momentum equation has got that kind of dependence, right. So, based on this x and y dependence, can we merge them into one single variable? Okay. So, that would mean, okay, so there will be no x and y, there will be only one variable across which we can describe these profiles. Okay. So, in other words, okay, we propose what we call a similarity variable. Okay. So, the similarity variable, what it should do? It should absorb x and y variations into a single transformed variable. Or in other words, we can convert this PDEs, if you look at the PDEs like this, we can convert this PDEs to an ODE, right, because x and y dependence, essentially x comma y is merged into a single variable, say neta. Okay. So, if we can do this, then this particular equation ideally should get reduced to an ODE, right. It can be non-linear, does not matter, but we should be able to go make it down to an ODE. So, there is one single dependence of u or v, okay, with respect to neta. Okay, the other variables, and that is possible because of the reason that we can stretch these profiles, okay, across x, right, across x, these are different x profiles, right. So, there may be a possibility by which we can actually achieve this. Okay. So, we will not go into the historical perspective of this whole thing. Okay. This was this is known as the Blasius solution essentially. Okay. So, let us propose a similarity variable. There are several ways of doing this. So, not sure if Blasius did it in this way, but we will propose it like this. So, let us say y neta equal to y over delta, okay, and we already saw that delta scales as x to the power of half. This we already saw from our last scaling argument lecture, right. So, all we have done is nothing, we have just taken a new variable neta and every y we are dividing it by this delta. So, delta actually varies because delta is a function of x, as we see that it grows, right. So, at every y location we are basically normalizing it by the corresponding boundary layer thickness at that particular location, right, something like that. Okay. So, neta, if you substitute also for the form of delta from our scaling argument, if you recall the scaling argument, that is why the scaling argument was so so good. Okay. So, if you substitute delta in this particular way, right, delta if you substitute in this particular way, this is the form that you get, right. Okay. So, this actually absorbs x and y variation into one variable neta, but we do not know whether this transformation will hold water or not till we work out the full solution and see that whether it really transforms the momentum equation from a PDE to an ODE. Okay. That is the proof, right, will hold if and only if the momentum equation is reduced to one single variable. Okay. So, let us assume a few things, u by u infinity, where u is the parent variable is f neta, v is equal to u infinity into gamma by x into g neta. Okay. If you look at it, some transformation rules we can establish. It is very simple actually, just this is a lot of algebra. So, just bear with me with the steps, right. So, let us establish d neta by dx, for example. Similarly, your d neta by dy. Okay. So, these are standard math. Okay. There is nothing much to explain except that these are the transformations that you need, right, to convert the momentum equation from its x and y coordinates to the neta coordinate. Okay. So, that is what we are trying to do over here. Similarly, du dx u infinity similarly dv by dy these are some of the transformations which will come in useful, because we have to convert it to the corresponding neta coordinate systems. What will be the boundary conditions will look like? The boundary conditions will be, say at y equal to 0, neta goes to 0, right, because of this, pay attention there, neta goes to 0. Okay. So, that would mean that u goes to 0, okay, which will lead to f0 becomes equal to 0, correct. That is the first argument. Y equal to infinity, neta goes to infinity, f infinity becomes equal to 1, right. As y goes to infinity, neta goes to infinity, f prime infinity goes to 0, right. Okay. Okay. And why this happens? That is because your du dy, okay, goes to 0, right, at the edge of the boundary layer, right, because there is no more variation with respect to y at the edge of the boundary layer. Okay. So, these are your basic boundary conditions, okay, once they are converted into the corresponding neta coordinate systems. Okay. Now, with these rule set, right, this is the transform variable, right, these are the u and the v expressions, these are the corresponding transformations using chain rule, right, these are the corresponding boundary conditions, right. Now, we are in a perfect situation to take the continuity equation first and then shift to the momentum equation. Okay. So, let us do the continuity. Or right, because u infinity by x actually takes off. Okay, so, g infinity prime okay. So, you can see this is the expression. Now, here let us propose something looking at this particular form of the equation, that if f neta becomes equal to f prime neta, okay, this is just a casting, different way of casting that thing, and then if we substitute it here, how should it look? Okay. So, in other words, then u by u infinity becomes equal to f prime neta, not f neta, okay, based on this particular transformation. Why we will do this? It will become apparent in a second. So, based on this transformation, what we have is that g prime becomes equal to half neta f double prime, right, that is what it becomes. Okay. Now, if we integrate this particular guy, this is g prime d neta, okay, is equal to neta by 2, right, that is the integration. This will give you g half n f prime minus f. You can see why this transformation has helped. That is because of the simple reason, right, we would have otherwise dealt with an integral of f neta over here, capital F neta, okay, instead of this small f over here. Okay. So, it would have become a integral, there would have been an integral within this particular bracket, right. Okay. So, here of course, the offset or the constant of integration is a constant and is 0 here, got it. So, what we got from the continuity equation, g equal to half of n f prime minus f, right, where f prime neta is basically nothing but u by u infinity, right. So, u by u infinity was f prime neta. Now, let us look at the momentum equation, right. So, look at the x momentum equation. Let us put the terms in. This is a full expression as you substitute all the numbers. Okay. Now, you can work out the algebra. I am not going to do it over here. If you work out the algebra, it will give you neta f prime minus f double prime minus neta f double. Okay. Or we can simplify this a little bit, plus half f double prime is equal to 0. So, this becomes an ODE with neta as only variable. So, this is correct, right. So, then we have been able to reduce the momentum equation to an ODE with a single variable only, right. The nature of these equations are that it is non-linear, it is third order, that means 3 boundary conditions are needed. So, 3 BCs are needed, got it, understood. So, this is the parent equation, that is what we are going to solve, right. Remember always f prime is u by u infinity. Okay, clear up to this particular portion. So, there are 3 boundary conditions which are needed. So, what are those 3 boundary conditions going to be? Let us write it down here. Okay, y equal to 0, f prime is equal to 0 because u is equal to 0, okay, and neta is equal to 0. Okay. Similarly, g equal to 0 implies neta f prime minus f is equal to 0, therefore, f is equal to 0. Okay. Third boundary condition will be y equal to infinity means f infinity is equal to 1, f prime infinity is equal to 1. Okay. So, these are the 3 boundary conditions that we have. So, y equal to 0 means essentially the no slip boundary condition, okay, that we have. Okay. So, it also implies that g equal to 0, because if you look at the definition of g, right, if you look at the definition of g here, if you look at the definition of g, that is right there. Okay. So, when v is equal to 0, g also has to be equal to 0, right. So, also comes from the no slip boundary condition. Okay. So, that would mean that g is given by this is equal to 0, f prime is already equal to 0. So, f will be equal to 0, that is one other condition. Then y equal to infinity, okay, that would mean that f, this big F is equal to 1 because u approaches u infinity, right. So, that would imply f prime infinity is equal to 1, got it. Okay. So, basically let me compile it in a more cohesive fashion. Okay. So, y equal to 0, neta equal to 0 gives rise to f prime equal to 0 and f equal to 0. At y equal to infinity, okay, f infinity is equal to 1, which implies f prime infinity is equal to 1 because u approaches u infinity, right. Here of course, u becomes equal to 0 and v becomes equal to 0, right. So, these are the boundary conditions that we have, right. Now, y equal to infinity now poses, if you want to now solve this equation, right. So, there are, this is an ODE with 3 boundary conditions which we already have. One boundary condition is at the wall, the other boundary condition is at infinity. So, y equal to infinity poses a problem, correct, because this boundary is at infinity, that is the problem. Okay. So, what people use, they use normally something called a shooting method. What is a shooting method? In this method, okay, so use something like a shooting, there can be other types of methods also. It is a shooting method is particularly useful. Okay, in this method what we do, okay, it is assumed actually, assumed that f double prime 0 is equal to sigma, okay, and each sigma, this is not gamma though, this is sigma, okay, where each sigma, okay, will yield f prime neta as neta goes to infinity. Okay, so, this sigma is such chosen, okay, that in the limit neta goes to infinity, f prime becomes equal to 1, right. So, that is how we choose, okay, in this limit. Okay. In reality, of course, in reality, okay, neta is assumed to some value neta infinity is fixed arbitrarily, okay, such that f prime neta approaches 1, okay, when neta is equal to neta infinity. Okay. So, that means once again it is an asymptote, okay, because f prime neta is once again the same thing, right, it is u by u infinity. So, when u approaches u infinity, that is where you kind of truncate this whole thing off. Okay. So, but ideally what you do is that basically it is a guess approach, that means you fix a value, you do the solution, okay, that means you reduce the boundary to something like n equal to n infinity, okay, and see whether the solution kind of merges or not. So, it goes back and forth. Okay. This is not a numerical class, so you can find different ways, okay, if you just do a thorough search, you will find that how are the different ways by which we can actually solve this. Okay. So, based on this tau wall is given by du by dy at y equal to 0, right. That is the definition of the wall shear stress. Remember, wall shear stress comes into account to find out the drag, right, that is the utility of the wall shear stress. So, mu into u infinity into root over u infinity by gamma x into f double prime 0, right. Remember, f double prime 0 is basically nothing but the slope of the velocity, right, because u by u infinity is f prime. So, f double prime is basically u by du by d neta essentially. Okay. So, this part was already established, if you look at it, it is already established through the scaling. We already know this part, correct. This part is already there, we nailed it in the scaling. This is the part that we need, right. This is the exact part. Remember that coefficient that we said that was missing, that cannot be answered from scaling argument, that is this part, right. Okay. So, this part's value actually comes out to be 0.332 if you solve that equation using the shooting method. Okay. So, that is how it comes out. Okay. So, as you can see, so by utilizing this you can find out that value of the wall shear stress, and you can also find out the exact term, that is that 0.332 which sits in front. Okay. Now, you know an exact answer to the query. Now, let us see that how the solutions actually look like, right. Now, that we have done all these things, okay, let us look how the solution looks like. So, let us look at the PPT over here. So, in fact, in this particular PPT, okay, we can see a few things, okay, over here. So, let us look at the next slide perhaps, because that would give you guys a idea. So, this is basically your f prime graph that we have plotted, okay, f prime, as you can see, okay, once again using the shooting method. So, f prime was what? F prime was nothing but u by u infinity, that is f prime, right, that is what I have written over there, right, and this is plotted as a function of neta, a variable. So, what do you get? You get that after some time the f prime gradually asymptotes like this, right. So, when it is equal to 0.99, our usual estimate, right, we basically say that that is the end of the boundary layer, right. So, that value of neta comes out to be around 5, got it, that value of neta comes out to be around 5, Okay. So, it agrees. So, once again this particular factor we would not have been able to determine just by scaling argument, right. So, by using this particular form we now know that that factor is nothing but equal to 5. Okay. So, that is your f prime neta, right. Let us look at the second one, which is basically nothing but the shear stress, right. The second derivative is nothing but the shear stress, right, f double prime neta. Okay, and it is evaluated at 0. So, this is the general thing for tau. Okay, f double prime at 0 is basically is equal to your tau wall. The shear stress is always there, that is tau, right, but this gives you the wall shear stress, right, and that value as you can see over here is 0.332, which we just now mentioned, right. As you can see, okay, from here to here as we go on outside the boundary layer, what do you see about the nature of this particular profile? You can see that the shear stress approaches 0, right, which is legitimate because you are going to the free stream now, right, because there is no gradient of velocity that is remaining, right. So, it should be the opposite of the u. As u approaches u infinity, the shear stress approaches 0, right, and shear stress at the wall is nothing but 0.332, that is the factor. Okay, that is that additional factor that comes out, which cannot be found out through the scaling argument, right. This is we already did, we already showed, right, okay, this particular thing. And if you look at now the f is actually related to the v. So, we will consider this a little later, okay, no need to consider it now, but we just gave a graphical overview that how this is actually done. So, let us move into our Windows journal form, okay. So, where we actually said that this is what the profile should actually look like, okay. So, now that we have done the scaling of momentum and we showed that what are the exact numbers and we have shown how the profiles actually look like, the natural next step will be to look at the energy equation and establish a similar scaling, not a similar scaling, similar similarity solution for the same, okay. So, let us look at this in the next lecture.